scales. But for the next couple of decades, everyone just focused on the spatial scale. So despite what you might have learned from Star Trek, space is not the final frontier in our understanding of the environment. I actually think it's time. And so I'm going to show you some of the things that we've been thinking about for the last year. So the understanding of how species are arranged across geographic space has actually led some folks to even question whether communities, ecological communities, exist as a thing that we can see or know. And I love this quote by Bob Ricklefs that the study of communities should be replaced by the spatial distributions of populations, which are now the primary focus for understanding biodiversity. I would argue that similarly to what Bob says about species across, or populations across space, communities are also temporal distributions of populations. Folks like George Jacobson have helped us to understand that. And this is a really great example from Tower Lake, which is the first lake I record. And you can see here that over the last 9,000 years, there's no one main or natural community for this site, even though there hasn't been a ton of environmental variability at this location through time. You can't necessarily point to any one of these ecological communities and say, okay, yes, this is the natural community. So there's been a lot of dynamics. And this is not a new idea. For over 100 years, we've had an appreciation of communities as dynamic entities. Henry Chandler Cowles, working on the Indiana Dunes, said vegetation is a variable approaching a variable rather than a constant, which I love. And yet, even though he said that over 100 years ago, so much of what we think we understand about ecological communities is based on ideas of equilibrium or short-term time snaps. And a lot of our understanding of how communities form or assemble is kind of arm waves ideas of time, but we don't really address them explicitly. So this is a model of community assembly where you have some species from the regional pool. They have to go through some environmental filter. There's some biotic interactions, and then they kind of sort out into ecological communities on the other side. But well, time is kind of implicit all over the place in a diagram like this, but we kind of just throw our hands up and ignore it for the most part. Even though we know that the regional species pool itself is going to vary with time, we know the environments are variable, which is something that's often ignored. So I think we need to really insert time in a more formal way into our understanding of ecology. And we know that time modulates the ecological drivers and also the responses, both in a relative way and an absolute way, in terms of the time scale of these climatic processes that we're interested in, the time scales of these disturbance processes, and then the time scales of these ecological processes. And we study these on short-term scales, on quaternary time scales, on deeper time scales. But one problem is that the reference timescales we use may not actually be appropriate for the processes that we're trying to understand from the record. So everything from deep time paleofaunas and floras to Pleistocene floral and faunal records, et cetera. But if you look down here, the laser's not working. If you look down here, these processes that we're really interested in are kind of in this middle domain between modern studies of communities and some of these deeper time studies. And so some other important things to keep in mind is that the temporal extent of our understanding is also going to have implications for our inferences. So let's say you have some observation here where you see a population on the increase, maybe it's a fishery. Well, we don't necessarily know if that's part of some kind of cycle, if that's a long-term, or if it's a sudden deviation from a long-term norm, or if there's some variability and we're moving outside of that natural range of variability. Similarly, the temporal grain of our ecological sampling, and this extends beyond just ecology, any kind of time series, also has implications for our inferences. So let's say there's some phenomenon of interest where maybe you have a population crash and then a recovery. If you're kind of sampling across that interval, you might be missing the event that you're really interested in. Similarly, you could be time averaging and coming up with a very different conclusion about the dynamics of that system. And sometimes that's okay if what you're really interested in is that longer term pattern, but it's just something we have to be aware of. Similarly, we know that the environments are highly variable. They're variable across timescales, and they're variable across ecologically relevant timescales. So you can see here, there's a 1,200-year time series of annual precipitation. And if you just zoom in on the last sort of 100 years, there's variability at the short term, there's variability at the long term. And communities are responding to that. And if you zoom out to longer time scales, it's really hard to actually point to any one climate normal or mode for the Quaternary. And so being able to say, these communities are responding to some equilibrium or stable state in the environment is going to be fraught with errors. And so, most of the ecological theories that we've developed are on these very short time scales and often very short-term observations, maybe a 3-year study. Most of our long-term ecological research that doesn't involve paleo data is at the most a couple of decades long. And so this is some classic pollen-based work that shows that today spruce and ash don't have overlapping ranges, but we know if we were ice age ecologists 13,000 years ago, we would know that not only would there be a giant ice sheet taking up half the habitat, but also that these ranges would be quite different, and the relative abundance of these taxa would also be different. So any kind of predictive ability that we have for explaining modern communities should also be able to explain these kinds of patterns, and we haven't really done that kind of rigorous testing. Similarly, we know from the paleo record that novel or no analog assemblages often arise from highly variable environments, because every species very individualistically responds to these changing conditions. This is not true just for plants, but also for mammals. That orange dot represents a cave where all 3 of these taxa were found coexisting for quite some time during the late Quaternary. And then, of course, during the Holocene, these 3 taxa now have very segregated ranges across space. So our inferences, again, should be able to pick up these kinds of patterns or explain these patterns, and not just the modern snapshot or the paleo snapshot. Similarly, we know that the full range of climatic conditions that species can live in is only, we're only really witnessing a subset of those conditions. Going back over the last 15,000 years, we know that the realized climate space has shifted as new climates pop on the scene or drop out. And yet the species that we have today that are ice age survivors have experienced that full range of climate variability, but we're often only thinking about them in terms of what they're actually experiencing in the modern system. We also know, this gets at something George asked yesterday, that life histories will influence how species experience their environments. So for example, for many juveniles, they have a much narrower environmental tolerance than adults. And if you impose that on a highly variable environment, that's going to affect when you can get species recruiting or persisting, especially in these highly variable systems. And we also know, as Ben was explaining yesterday, that you can sometimes see lags or disequilibrial dynamics where the community is not doing necessarily what you would predict based on the environment. And we might expect to see those kinds of dynamics for species with very long lifespans, perhaps, that can ride out suboptimal conditions, or if you have dispersal limitations, or if you have very rapid change, it's just outpacing the capability of species or their assemblages to keep pace. Hopefully you're not lagging the rapid talk that's happening right now. So we also know that there's a wealth of paleo-environmental data, these long-term data sets that provide really neat context for identifying critical transitions, and these abrupt changes are increasingly of interest. There's been a lot of great work through the IGRT program on that topic, and you can see here a great example of the mid-Holocene hemlock decline, where we lose hemlock throughout its range around 5,500 years ago. So these abrupt transitions, I think, can give us some really cool context that we can then try to use to predict when these critical transitions or these threshold responses might be coming in modern systems. And I think there's a lot more scope to use paleo data to try to vet some of that theory that's really being based on modern observations. But again, we have these long time series of climate data, ecological data, where we can try to identify these abrupt changes. Sometimes, though, nothing happens for really long periods of time. Like if you look here, we have almost 14,000 years of what looks like stasis in this ecological community. And we don't really have a good handle on understanding whether that's a lag, whether that's resilience in this system, or some kind of extinction debt that hasn't yet been paid. So we need to do a better job of paying attention to things when they don't change, because sometimes there's an interesting story there, instead of looking at this and saying, oh, nothing happened for 15,000 years, that's boring. We also know that there are historical legacies that are really important. Contemporary populations often show the fingerprint of historic processes. This is a nice study that shows how pinyon pine recruitment was really linked to these episodic climate events. So even though climates aren't necessarily favorable today for pinyon to establish, there have been periods in the past where it has. And so there seems like there's a disequilibrium going on there. So these historical contingencies matter. How far back do we go? It's a really good question. Often we go to European colonization, where we know that historic land use and recent climate change have actually shifted the relationship of a lot of species to their environments. This is just looking at tree-climate relationships in the Midwest. So there's a fingerprint of European land use and recent climate change. We could go further back to the Pleistocene megafaunal extinctions, where I've done a lot of work showing that there are ecological legacies on modern communities even 10,000 years later due to the unique properties that these large herbivores played in their communities. You could go even further back to Quaternary glaciations, where we know that the influence of late Quaternary climates are just as strong as modern processes in structuring floral communities in many cases. Which is really amazing to think, like something that happened 10,000 years ago or more could be equally important in explaining what you see on the landscape now. You could go further back. Why not to the KPG impact that killed off the dinosaurs, where we see that there's a shift in the floral communities strategies from slow growth to fast growth. And those rules that got set up 65 million years ago may have implications for what we're looking at now. So where do we go from here? We need to study more systems across nested timescales to really get a sense of how these properties emerge as you kind of zoom in and out. We need to develop a better framework to understand how different drivers might set up an ecological community as you move through time. We need to start borrowing, as ecologists, more of the tools that folks use in climatology to understand these time series, because I often talk to people who have long-term data and have no idea how to analyze it. And that's something that paleoclimatologists have been doing for a very long time. And we should build a better framework to identify the importance of these historical legacies and contingencies on our modern systems and understand that they really matter. And with our focus on all these abrupt changes and critical transitions, we should also pay more attention to stasis, because we could be missing some really interesting information about the resilience of some systems that don't change when we expect them to. Thank you. Do we have time for a question? Anybody? Is there a question? Another question? Thanks.
Next is Katherine Glover with the talk, Vegetation Cover and Climate at the Rancho La Brea Tar Pits, Southern California during Marine Isotope Stage 3.
Is there a clicker up there? Should be
So hi everyone, my name is Katie. I'm postdoc in Jacquelyn's lab. I've really enjoyed the symposium so far, so it's my privilege to be able to talk to you about, I think, the part of the world we haven't visited yet, and where I'm from, which is Southern California. So I was hired to work on the La Brea Tar Pits, which was sort of a nice continuation of spending 6 years working in Southern California. From a recent review paper, this is sort of a map to get oriented and see where a lot of the continuous paleo records come from in this part of the world. So we've got California, a little bit of Mexico, Great Basin, and the Mojave Desert as well. My dissertation site was Baldwin Lake, east of LA, up in the mountains, east of the metropolis. And how many are familiar with La Brea Tar Pits? This is right inset in the LA metro area, so I highly encourage you to visit. I think the average or approximate count of how many specimens they have is 5 million cataloged from Pleistocene animals, extinct megafauna, and the focus of this project is to try and round out that picture to get some of the plants and small mammals that lived on site too. So a little bit about the tar pits. There's many, many reconstructions of what was happening to cause these entrapment events. Saber-toothed cats have been found at the site, mammoths. Excavation started in 1915, and like a lot of older archaeology projects, the focus was very much on that charismatic megafauna and the carnivores at the site. And I think a nice testament to sort of that style or approach is at the back wall of the museum, they have all these dire wolf skulls lined up and lit up from the back, covering a whole back wall of the 70s era museum. Excavation's a little bit different now and a lot more careful. Right now it proceeds with these different boxes that are part of a salvage project that came from a construction site next door. There were fossiliferous deposits. So these are put into tree boxes and then moved over to the site, and now excavation proceeds pretty carefully. So this is a couple team members at the site and myself with volunteers working on the excavation. And pretty much everything is cataloged now and recorded exactly where it is in situ. So that's the material that we're working with for this project. And broadly speaking, the project asks, how did communities change over time? Are they resilient to climate change and perturbations that happen? And what's the composition and structure of these communities? Do they change through marine isotope stage 3? So I thought I'd go over the structure of the whole project. There's probably maybe as many 20 different folks working on this project between postdocs, PIs, undergrad helpers, and graduate students. It's an NSF-funded project with some of us here at UMaine, some at UC Merced. So I mentioned there's these boxes that get excavated. The scope of our project is about 5 of them. And this gives a rough sense of where they are in time. One of the problems with this site is law of superposition does not apply to the tar pits. So things move underground after they get deposited if seeps reopen. That makes it really challenging. But doing this box approach helps us at least constrain each deposit to at least a few millennia. So we have an idea where it falls during either stage 3 or the last ice age. Most of these boxes are pretty firmly in marine isotope stage 3, and that lasted 57 to 29,000 years before the last glacial max. Focus of the project, we have a lot of expertise on plants and small mammals, so we're interested in how they contributed to the community. A couple pictures that have been produced by the project so far. And then from that, we can hypothesize what feeding relationships existed, vegetation modeling to try and estimate ground cover at the site, and then get these outputs of how much primary productivity happened, how much nitrogen is available for the system and the rest of the food web. And then having a digital food web model of what's going on at each of these different assemblages gives us something to digitally play with a little bit. We can remove one species that we found and see how does the community readjust? What are really those keystone species? How resilient is that whole food web to change? My role in the project is to do the vegetation modeling. So we use a dynamic global vegetation model approach. Anyone who works in the C++ environment or has familiarity with downscaling, I'd love to talk at some point. This work is in progress and sort of a new venture for me after being a lab scientist for a long time. But a lot of our regional parameters that I'm interested in collecting right now and downscaling include appropriate paleotemperature curve, carbon dioxide and how that changed throughout stage 3. And then that's going to drive the model and kind of what we find was there for the ground cover. I figured I'd talk a little bit to this audience about a side project that I've worked on too that sort of fits my background more in paleoclimatology. And no one has systematically looked at all of the radiocarbon dates taken in the collection so far. And I'm so glad yesterday's guest speaker set the stage for histograms and like looking at radiocarbon dates in aggregate. I think this is a really neat way to at least sort of look and see what kind of patterns are happening in a region based on, in this case, when are a lot of animals apparently getting entrapped? When are we getting material that dates to certain times? Most of the dating now for the project is done at UC Irvine in the Keck lab. If anyone knows John Southin, who runs the lab, he's a little obsessed with the tar pits, and so happy to run a lot of samples for us. Nearly 500 have been dated at the site so far. I'm interested in knowing if organism entrapment has this apparent match to climate change that's happened in Southern California over time. Studies that have come out in the last few years are really showing that we've heard kind of these qualitative statements about Southern California ice age, that it was cool and moist or cold and dry. But we're starting to get these really high resolution records. And I'll start with stage 2 just to show recent site Lake Elsinore really nailed down this time where there's a mega drought, 2,000-year drought. Stage 3, again, is usually described as broadly cool and moist. It's one of these interglacials that's not quite as warm as the Holocene or stage 5 before. But as we get more sites, maybe that will show that it's dynamic as well. And then I've overprinted here kind of the hallmark of stage 3, of course, are the North Atlantic warming and these Dansker-Dashker events, interstadials. We know for sure these register pretty strongly in the Santa Barbara Basin with rapid warming. What the terrestrial response is, if it's colder, drier, wetter, warmer, that's kind of an unknown. It's a question I'd love to solve with my career, but it's kind of an unknown, but there is the potential for this dynamism. First pass at looking at the radiocarbon dates, once we rule out some of the ones too old and too young, there are about 300 or so. And you can see that this is dynamic as well. Entrapment is not a continuous phenomenon that seems to happen across about these 40,000 years of time. And I'm most intrigued that right at the start of Lake Elsinore drought, apparently we have this spike and then entrapment stops. So either asphalt seeps aren't working or perhaps animals just leave the LA basin altogether. And then just a reminder where our project falls, hopefully this will start to round out the picture of what's happening down here. We have, I think these are actually the existing box 1 dates that's centered around the Camel deposit. But with more work on the project and some of the dating we plan to do, hopefully we can round this out and see, is there dynamism down here as well with when entrapment happens. So just in summary, you got a sense for how the whole structure of this project, our focus on some of the more local critters that lived at the site, and the dynamic global vegetation modeling is its first use in a Mediterranean biome and at this time in stage 3. And then preliminary cluster analysis of these radiocarbon dates show there's a pretty complex history of entrapment that seems to fit with this emerging picture that the climate is dynamic as well and subject to at least rapid changes in hydrology that happen across stage 3 and then all the way into the LGM. So with that, there's a lot of outreach that's part of the broader impacts for the project. There's a Twitter handle you can look up that'll lead you to the project blog and some of the other products that sort of talk about the site ongoing and what the different members of the project are doing. And then I'd like to acknowledge our funders and CCI as well. So thanks for listening and happy to take any questions. Yeah.
With the initial early excavations of the early 20th century, were they just getting rid of small mammal bones and like macrofossils of plants, like they just threw out?
I would assume so.
That's crazy.
Yeah. It was 1915 or so it started. I mean, that was the era. You see something you hadn't seen before, or that was instinct. That looks the best in the museum. So that's what they focused on. Yes.
Can you talk a little bit more about the boxes?
Sure.
So how are the materials, how are they excavated into the boxes, and how can you be?
My understanding is like they were cut out in situ. So the museum is located in this Hancock Park, and there's actually an art museum next door. Art museum wanted to build a parking garage subground. So these were kind of cut out in situ, wrapped with foam and the wood of the tree box, and then moved by crane over to the other part of the park that's under the management of the tar pits, and they manage the excavation of those boxes now. And actually, to answer your question, Caitlin, we'll come back. There is some plant material and such that's been recovered, but it's pretty understudied. But I think there's a little bit of work that's been done from 40s or 50s or so. That's part of the collection. But again, a lot of just the showier stuff was kept. Yeah.
Is there a big history of tar production throughout the structure? Because I imagine if you have more tar in landscape, you get more intricate. Is there any way to work out the rates of tar production?
That's a really good question. My sense is that's not really well understood. And even talking to the managers at the museum, they'll just say things like, well, we know tar seeps opened up and closed up over time. But in terms of an exact chronology, we don't know. That we actually might get a better picture of that once we radiocarbon date the individual boxes and can kind of see times when it seemed to be more active than not. Anything else? All right, thanks so much.
Well, it's a pleasure to be here. I'm a computer scientist. I'm in the School of Computing and Information Science. And I've been working with Jim Fastook and one of our grad students, Christopher DeFore, on basically looking at computational costs of various approaches to large-scale modeling. Unfortunately, Chris, as we speak, is out interviewing for a job rather than staying as a PhD student. So I'm sorry to see that. But so we're looking at the issue of modeling, polar ice sheets, very large scale systems. And the problem that you get from these kinds of systems is the sheer size of the domain. It's a very, continent level domain. It's very large. And also the need for high resolution. There are parts of the glacier that require high resolution modeling, parts that don't, but that makes it a difficult problem. So there are two basic approaches that have been used in this domain. Historically, the ice sheet modeling community used finite difference methods that were applied to structured fixed size grids. More recently, they've been introducing finite element modeling approaches where you can have unstructured meshes rather than fixed sized grids. And that allows you to create dense areas of the mesh where ice flow dynamics are critical and coarser areas of the mesh where they're not as critical. And so my concern is how we map these approaches to the current state-of-the-art supercomputing systems. And the primary qualification, I guess, of these kinds of modern systems is that they're multi-core systems, which means that architects, rather than trying to continue to increase the speed and performance of a single CPU, have rather decided to place a lot of very simple CPUs in the same node. Okay, so those are the multi-core systems. And they have a big impact on the ease with which these different approaches, can be efficiently executed. Structured grids, and I think, probably the reason they've been used for so long, is that they map really easily to this kind of architecture. Okay, the data is stored out as contiguous arrays of data in memory, and that creates a lot of very positive computational magic, if you will. In particular, it makes very good use of the caching system, which can make a significant impact on the performance. And also, it allows the use of the hardware vectorization that's available on modern supercomputers. It also is nice because generally, neighboring nodes are in close spatial proximity, just the way that these problems are decomposed, which reduces the communication cost between the nodes. It provides a very simple basis for efficient domain decomposition, i.e. mapping the domain to a set of CPUs. And it's really simple load balancing, which is an aspect of this project I wish I had time to talk about, but don't. But it makes a tremendous difference. The problem, of course, with using structured grids is that, because they're evenly spaced, you have to execute the whole model at the highest resolution you require. And in the case of, if you want to model ice streams at, say, 500-meter resolution, then if you try and do that over the whole model, you're looking at close to 7 billion grid points, which becomes computationally intractable, or at least difficult anyway. Unstructured meshes are great in that they are able to capture multiple levels of resolution within the same simulation. They use the technique of anisotropic, I knew I was going to mess up on that one, anisotropic mesh refinement, where it's an approach where you generate high quality meshes while minimizing the number of vertices in the mesh. That can reduce computational cost. Because as I said, the areas that need, high resolution, you can actually allocate more CPUs to those regions than to the regions that are coarser and don't have the need for that level of resolution. So those are very nice aspects of using unstructured meshes. The problem is they don't lend themselves very well to parallelization across the current state of distributed memory parallel computing supercomputers. The primary problem is that there's a lot of indirection. There's a lot of accessing your neighbors by going through some kind of a pointer, that's keeping track of where all of your neighbors are located. And the problem with that is that it leads to irregular, unpredictable memory access patterns, which means your whole caching system is basically posed because that requires predictable access patterns. It also can have a very negative effect on being able to use the hardware vectorization that's available, because that requires that the memory be laid out contiguously. Domain decomposition is difficult. You have cells of arbitrary size with irregular connectivity. Trying to figure out the best way to map that to a set of processors is a very difficult problem. Because of all of the indirection, you've basically lost your spatial proximity. So neighbors, even though logically they're close, spatially, physically, they could be anywhere on the system, and that can lead to increased communication cost. The problem of having irregular partitions, can lead to an imbalance of what are called ghost cells used for communication between processes. And that kind of imbalance leads to significant load imbalance and also increased synchronization times. And load balancing is notoriously difficult to accomplish on unstructured meshes. So what Jim and I have been working on is a different approach based on embedded simulation. And what we are attempting to do is to provide multi-resolution capabilities to a structured approach, okay, while we are preserving the computational efficiencies of using structured grids. And so the approach basically is to embed high-resolution models of areas undergoing rapid change into a low-resolution whole ice sheet model, okay? Our approach is based on PISM, parallel ice sheet model. Each of the models is a independent, fully parallelized PISM model, although we've added communication and synchronization mechanisms to maintain the fidelity of the simulation. And in high performance computing, it's really important to have a name for any system that you develop. So I came up with ELSIM for embedded simulation for large scale ice sheet models, which I thought was about as good as I could do, at least, at least on that day anyway. Okay, so here is kind of an overview. This would be your structured high or low resolution simulation, and then an embedded high resolution model. This is what it looks like. Logically, you've got two separate simulations. They're communicating using the message processing or message passing interface. And then we have a two-phase synchronization protocol to maintain the fidelity of it. So we compared our embedded approach to the ice sheet system model, which is a very well-known, widely used model developed and maintained by Jet Propulsion Laboratory in UC Irvine. It has a high-quality mesh generation tool that uses anisotropic mesh refinement, again, to create high-resolution meshes with minimal numbers of vertices. Okay, so because it's possible, or because the mesh generation tools are so sophisticated and able to create high quality models with a lower number of degrees of freedom, it's difficult to compare grid points with number of vertices directly and come up with anything meaningful from that. So we gave up that attempt. We tried that for a long time. But we finally gave up, and rather we started looking at the scalability characteristics of these approaches across a wide range of problem sizes and core counts. So we use sea-rise and Croesus data. For ELSIM, we embedded a 500-meter Jacob-Schaven model into a whole ice sheet model. And we varied the resolution of the low resolution model so that we generated between 350,000 and 2 million grid points. For ISM, we used their mesh generation tool and varied the parameters to create meshes with between 75,000 and 1 million vertices. We were interested in looking at the strong scaling efficiency of the approaches, which is essentially a measure of what percentage of linear speed up is obtained, okay, as you increase the number of processors and keep the problem size constant. Problem size constant. Okay, so I'm jumping to the conclusions here. I'm getting harassed. So these are the scalability results for ISM, and what we're looking at are these are the problem sizes. We used between 128 and 4096 processors, and each of these bars represents the percentage of linear speed up that was obtained for that problem size and that number of processors. So what's interesting is that it does very well at smaller problem sizes and smaller node counts, but it's not able to take effective use of large core counts for any problem size, and the whole scaling goes south for large problem sizes. So it doesn't have as good a scalability characteristic. It's not able to take advantage of more processing power. With ELSIM, I'll just show that, you know, the scalability metrics were much better. We were able to take effective use of all the way up to 4K processors. The thing that I think is the coolest about it is that the scalability results got better as we increased the problem size. Okay, so that's a pretty important characteristic as well. The other thing we measured was the cache hit rate, which is the percentage of memory accesses that are serviced at some level in the caching system. And for ELSIM, we got a 95% hit rate versus about 85% for ISM. And we're interested in looking at why ISM performs poorly at large problem sizes. You know, is it a communication problem, load balance problem? So we'd like to figure that out, and we're working to implement multiple high resolution models in ELSIM, and I am done.
Hi everyone, I'm Beth Hufnagel, and I'm going to shift gears quite a bit, as you can see from the title of my talk. I'm an assistant professor of science education in the College of Education and Human Development, and my research area largely is on the ways in which science is learned and taught in various science learning settings. But what I'm going to talk about are emotions and the ways in which learning is emotional when we learn about climate change. It's very hard for me to think about condensing my program of research to a new audience in 10 minutes. So I'm really going to probably leave you with more questions than answers. So I kind of offer that as where we're going. So you can see here, I examine emotions, and I do that in the discourse of science education settings. So what that means is in the language, whether it's talk to text, and the various ways we do that in relation to global climate change. I look at other issues too, but global climate change is, well, a passion of mine. So it's helpful to kind of orient you to my thinking of what emotions are, because we often use this word loosely, and even happens in research. So my work is very interdisciplinary. I draw from social psychology. And yes, this is a very dense definition, but I gave it to you purposefully to unpack it. So Keltner and Gross are social psychologists, and they theorize emotions as biologically based patterns of perception, experience, physiology, action, and communication that occur in response to specific physical and social challenges and opportunities. Okay, where are we going? Well, to start with, everyone has that. In addition, they're about something specific. And actually, that's what I find so interesting about them, is they indicate a deeply personal relationship with something. If you're not emotional about something, and really, you don't really care about it, it's not deeply personal to you. So when I think about climate change, I want to understand how learners find climate change deeply personal. And I actually want to also explore that with teachers too, which I do. In addition to being about something specific, they are evaluative sense-making mechanisms. They evaluate information and experiences in relation to our own goals. So they're indicative of what we care about and why. And the way in which I theorize emotions is that there are no good or bad emotions. To me, any deep and personal engagement is indicative of caring. And we put labels on certain sets of emotions as positive and as negative. And that's really because of that evaluative piece. So when information or experiences either maintain or enhance our personal goals, we experience happiness or excitement. When our personal goals are inhibited, we feel things like frustration, anger, sadness. So I hope then you can start to see, oh, how does this connect to learning about climate change? Well, there are different things that people take really personally about learning about climate change. So to me, I would just point out this aboutness feature of emotions. It's what the emotion is about. You're going to see this later in some other later slides. And finally, emotions are a form of communication. And as someone who studies discourse, I find that form of communication really important for thinking about ways to communicate climate change in classrooms, but also outside of classrooms as well. So why do emotions in climate change matter, or in climate change education matter? So we know that you can learn about a topic and really not just learn about it, take the test, and pass the test, do great actually, but still not actually care about it. So knowledge about climate change translates neither into caring nor taking action on the issue. And when I say taking action, it can be a whole range of actions, from lifestyle choices to even just the desire to want to learn more. Emotions, we know, play a mediating role in action, and emotions encapsulate the complexity of issues. And climate change, as we've seen from the symposium this week, the science in and of itself is deeply complex. So emotions are a way to capture some of that complexity. And the emotions inform our decisions about taking actions on environmental issues, in addition to how we perceive ourselves of being capable of making change. So I just decided to include a couple of recent studies to kind of give you a sense of what people are studying when it comes to emotions and climate change education. So the top one is about teachers. And these two researchers found a correlation between elementary and secondary teachers' anger about climate change and their ideas of a lack of plausibility of climate change. I think that's really powerful. Another study pertains to learning, and that's that relationship between students' hope and their perceptions of how teachers respond to their emotions is really important. And in that particular study, high school students who felt their teachers valued their negative emotions, anger, frustration, were more likely to feel constructive hope or action-oriented hope, rather than hope based on downplaying the issue, which many times is just called optimism and is not really based in an idea of doing anything about it. So for me, I study the ways in which emotions are expressed. And I look at that in the ways that they're used, shaped, shared, and through a whole range of ways that we express emotions. And I don't include a comprehensive list here, but I examine emotion words that are used, signs and symbols, especially in text, metaphors, because we actually largely talk around emotions most of the time, features of speech, tone, speed, emphasis, pitch, gestures, and facial expressions. I don't look at any of those in isolation. I look at all of them together, because even the same person feeling the same emotion expresses it differently, depending on who they're with and the situation. So emotions are a very situated phenomenon. So I approach them in such a way. So I'm going to highlight just one study I've done. It was with 30 students. They were all education majors. And they were about halfway through their program, most of them to be elementary teachers, but not all of them. And the university where I did this work, they actually had science courses specifically for education majors. And this science course was a climate change course taught by a paleogeologist, co-taught actually by a paleogeologist and a science education professor. So the data sources are all of the anything students wrote on or constructed on paper or video, I collected and analyzed, as well as 2 different sets of video recordings from every class meeting and field notes as a participant observer. And for those of you who love some analytical method, not in your field, I draw from interactional, ethnographic, and sociolinguistic approaches. So I look at the ways that emotions are expressed in the discourse in which they're expressed. So I don't use kind of Likert surveys, or I don't try to get physiological heart rate and such. So really quickly, a synopsis of the findings. I basically looked at all of the emotional expressions that all of these learners expressed throughout the entire course. And I broke it up in different ways. But a couple of slices I want to share with you kind of goes to this aboutness. What were the aspects of climate change that these learners in a climate change course were most deeply engaging with? And as you can see here, the impacts by and far were. And so as we kind of zoom in to what those impacts were and how they were making sense of them, we see that, let's see if I can get this thing to work. Yes, that they were really deeply emotionally engaging with, so there were a total of 78, other species and the impacts on other species, as opposed to the impacts on themselves or people. But if we look at this, more than half of these emotional expressions are about the impacts on species other than themselves and nature, and to kind of some degree, I mean, what counts as the planet when they say that? Is that nature, or is that kind of a, how are they conceptualizing that? So that's why that's shaded, but not included in the numbers. But what we kind of see here that's really interesting, at least for me, is thinking about the ways that people emotionally connect to the impacts on other species. Which, of course, then, as an educator, I also think, why are they not emotionally connecting to the impacts on themselves? What do we need to do differently for that? And another aspect is looking at the lack of action. And there are emotional expressions about a lack of action about climate change. And how did that kind of look? Well, what's interesting about this is instead of kind of this focus on other organisms and other species, the focus is on themselves and feeling and expressing this really prominent emotion of guilt, which was really fascinating. So 61%, more than the majority of the emotional expressions about a lack of action were in relation to the roles of themselves, personally not taking action. And guilt is really fascinating because it's about the desire to address specific actions that cause the guilt. So the emotion itself. And it focuses on the present or the past. So they were very in tune with what they were currently actually not doing that was basically them contributing to climate change. So in many ways, you could see how I could kind of go through each of these sets and kind of provide a large picture for what it looked like emotionally for them to engage with climate change. Knowing that I don't have a lot of time, I decided to just summarize. Oh, my beautiful picture is not showing up. Okay, oh, there it is. Okay, not so beautiful as some of the other pictures, but by looking at the way that they emotionally engaged with climate change, there is an interesting kind of set of tensions, and that's that a collective causes climate change. Again, this is what they found most relevant and personal. A collective causes it. They emotionally engaged with that others are impacted by it, but then they emotionally engaged with themselves not taking action. So it kind of creates an interesting way to think about how do people really deeply engage with climate change? And obviously I can go into a lot of detail around the course and what was taught, because that is important, and that is, that's how I usually write my manuscripts. But what I kind of wanted to offer today was maybe another way of thinking about emotions in the teaching and learning of climate change. Because I think largely what happens now is that emotions, especially when it comes to climate change, are framed as not useful. When if we kind of can think about, well, what is that person finding so emotionally relevant about the issue of climate change as we talk about it in public discourses, as we talk about it in schools, and as we talk about it in other spaces. And I think my big purpose, I'm realizing, is to have people realize, emotions are not scary. We've been socialized to think that they're scary. But if someone's telling you, conveying, communicating to you what's really important to them, that can help all of us educate people in ways that's relevant to them, and then hopefully have a more educated populace when it comes to climate change and understanding climate change. So thank you so much for this opportunity. Yes.
Quick comment and a question.
Yes.
Your last slide, it looks like the embodiment of the bumper sticker, think globally, act locally.
That wasn't on purpose.
But
I guess
maybe
it's
they haven't
always in
seen
my
that, it's in
mind.
there. But my actual question was, do you have data yet to know if the emotional responses are different between primary, secondary, and post-secondary students?
So not yet. I think it also, I have data to show that it also depends on the instructor. So the instructor plays a huge role in how and when emotions are validated in the classroom. And so if instructors don't usually make space for that, what does that mean for students? We can see in broader science education research that when emotions aren't validated, and this is actually broader to all educational research, students feel less connected and they largely turn off. So this is kind of an interesting space to think about. Then as instructors, how do we all make a little more space for that? Because this is a deeply complex and onerous, right? There's a weight to this issue and teaching this issue. Great question, thanks.
I have 2 questions, but I'll try to make them very fast.
Okay.
Can you move back in your slides to maybe like the 3rd slide where you're talking about some studies that have been produced, the teacher's anger?
Yes.
And I'm sorry, Beth, I didn't quite understand what that meant. So there's a relationship, a correlation between the teacher's anger and the lack of plausibility of climate change. What does that mean?
That means that they don't think climate change is real.
Okay, so they secondary teachers that express more anger in their instruction because they're angry that they have to teach it, or?
So not in their instruction. That was interesting about this study. So they surveyed the teachers. They didn't go into their classrooms and notice how if and how they were expressing anger, but they surveyed very large numbers of secondary teachers and they found multiple emotions, but they found this correlation between anger about climate change. Now, what does that anger mean? Because they didn't study the aboutness. Is it anger because they have to teach it? Is it anger because they're angry that this is a problem that hasn't been addressed yet? But I doubt it's that, because it has to do with the lack of possibility.
Okay, thanks.
Yeah.
The second one is in terms of the conclusions, I think this is really interesting that the frustration was associated with their lack of personal responsibility. And I wonder if you have considered, or if there have been others who have done this cross-culturally. Because what we know out of anthropology is that the way that I know a lot more about this economics, but the way that we teach economics really heavily structures the assumptions that people make about human nature. And in the US, where we have a very neoliberal state and a lot of focus on individual responsibility, I wonder if that's different than, say, for example, in Sweden, where responsibility is viewed in a much more collective way because it's been taught that way. So
There are some international studies that show some of that, but most of the studies really show ways that learners distance themselves from climate change. And so kind of my work is to kind of say, well, what happens when they're not? What are they engaging with? But I think that's a great question of what does that look like in different spaces and with different people? Yeah, thank you. Yes?
I was interested also in your assessment of the types of hope and what people are hopeful about.
Mm-hmm.
And in my case, I'm teaching a class of students where they, they're on board, they get it, and they believe in the science. And so I think the challenge is to end a class where you study climate change for a semester and not have them feel this sense of despair, but rather a sense of sort of action and galvanization to do something. And I was wondering if you have any advice on how to facilitate conversations about emotions that would help them transition those feelings.
So this is, I mean, it's a relatively new space, the work in general in emotions in science education. So I can't really say anything foolproof. Here's an evidence-based practice. But so many studies, kind of more and more, are showing that when students feel honored, their voices, their ideas, and emotions are part of that, that they are kind of more likely to not get stuck in that space of like the shutdown, right? So we have an emotion and it can propel us to action, and it can propel us to no action. I mean, there's a lot that goes on in between too. But in social psychology, they say you need just the right amount, and that's different for each person. So I agree that as a class, then, how do you mediate those questions or mediate those discussions? I think there needs to be a ton more research. But I think making the space for them to share their despair is important. Because in sharing that, they process what is despairing. And then certainly if it's done in a group, well, these are ways I kind of move on from the despair rather than just sitting with it, But it's the golden question right now, right? Is how do we motivate more people?
Build off of that, I taught a climate change class at Emerson for non-science. They're all non-science majors, right? There was non-science majors at Emerson, and we ended the course by bringing in an environmental writer, because I, as a scientist, felt like, well, the thing I can do is teach you guys climate change. But they really resonated to have somebody who worked in communication come in and talk about how they process their feelings around climate change. And this woman who came in and spoke to us, Bethany Taylor, had also been a high school librarian. She was very good at talking to kids in like freshman, sophomore age in college and getting them to reflect on their own feelings. And her message to them was like, now you have all these things to be angry about, but you have to enjoy the world that you have, and like here are the things that you can celebrate, and being able to balance feeling like let down by older generations, and then also feeling like, but we still get to live in this really amazing place in the world. So it was really helpful for me to recognize that I needed somebody else to facilitate that conversation.
Thank you for sharing. Yes.
I was wondering whether in your work or other people's work they found much evidence of these emotional reactions being distributed differently across ethnic groups. I mean, emotions are culturally reflected in different ethnic groups, different political views, which can also
Yes, absolutely. So, well, what's interesting about this group of students was that actually there were quite a few fundamental Christians in the group. And so that was, there were pieces, you know, if I could kind of pull them out, but their number was kind of too small to kind of say with any certainty, right? These are ways. But I noticed that there were tensions that emerged with students of that faith, because we talked, or the instructor talked a lot about evolution, but also climate change and spans of, as we've been talking about, right, temporal change and over how many millennia and such, and how that stirs and conflicts with worldviews, right? So it's kind of all there. I just don't parse it out, partially because of my method. I don't do large, 30 students is probably about all I can handle in one semester. Well, maybe, I'd like to grow that. But the methods I use are to look very deeply at what they're saying. But those are great questions. And it's absolutely true that everybody's expressions reflect not just their culture, but also the situation. So here we were, and it was truly a science class. And, so we could talk about the norms of expressing emotions in a science class compared to a literature class or something like that. So they're pretty different. But the students, it was really interesting, would often express emotions, and the instructors would kind of redirect the conversation. So I have another paper about the ways in which emotions were framed with this idea of the implications for how to teach in a way that makes a little more space for that, so that we can better understand what our students are engaging with deeply. And then so that then we can also help them work with those feelings that can be overwhelming at times.
Do you potentially have some examples of how we could bring the concept of emotion into communicating our own, say, physical science that is many times detached from that sort of thing?
Yeah. Well, I think that's what's so interesting is that, as scientists, obviously, there are lots of emotions, but in the communication, right, of information, that really doesn't come out. But I think often where maybe the space is, and I've worked with public health folks at Pitt, that's where I was before I came here, and we talked a lot about, in public health, you're sharing information and people's responses to it are emotional. And same thing with, natural resource management and communities and how they decide to make decisions around that. And same thing with climate change. So maybe there's more to understand that the emotional reaction isn't necessarily bad. It's actually maybe a good sign that they care. Maybe they don't care in the way we want them to, but I look at it as an opening rather than as indifference. Because indifference, okay, thanks. But if someone's angry about it, angry that, whatever that is that you're sharing with them Well, they're perceiving that as some form of injustice. And so what is an injustice? And orienting to that emotional space. So I don't know. I mean, that's a great question. I guess it would depend on what you're communicating and who you're communicating it to. If you have a sense of what that community's emotions often are, and maybe acknowledging them, just saying, it's okay to have emotions about this. But I don't know. It so depends. So sorry, I can't give you more specifics. Well, thank you again. This was a really great experience for me.
Hard to believe we've already reached the end. So just a few quick closing remarks. I want to thank all of the speakers for wonderful, wonderful, and truly interdisciplinary presentations over the last 2 days. Clearly, there is a lot of cross-pollination that goes on in the Institute, and it's good. Of course, as always, special thanks to Betty and Becky, who are the real force behind the Bourne Symposium. Without them, we wouldn't have this event, nor would it be as nearly as good as it is. So let's give them a big round of applause. Last comments. Our guest speakers were certainly very enlightening. Rolf Mandel showed us that less is more when it comes to understanding bioclimatic change in the Great Plains. Andy Cohen gave us deep insight into East African paleoclimate and the setting for human evolution. And Bess Kaufman gave a kick-ass presentation on the North Pacific. We heard a lot of cool things about ice. It seems that glacier studies are surging, and yet then paradoxically, they're not moving at a glacial pace, even if some of the results were a bit erratic, if you get my drift. Now, we learned about core issues in ice and lake ecology and paleoclimate, and we heard about hot new topics, such as thermal ecology. Susan Elias, who was this year's President Hunter Research Award winner at the Student Symposium, ticked off yet another achievement with her talk to us. Several of our other students were playing the old shell game. I could go on, but thank you all.